Hello, I am Atifa Darzi, a postdoctoral researcher at the University of Iceland. Today, I will be talking about the ground motion variability across a small aperture urban area during the 2008 magnitude 6.3 Olfos earthquake in South Iceland and its impact on seismic loss estimation. This work has been done by University of Iceland in collaboration with University of Alicante. This study focuses on 4 subjects related to the town of Kereyjardy, which is a test bed in the Horizon 2020 Turnkey project. First, high-quality waveforms recording of the May 2008 Olfos earthquake, which was recorded on ice array stations. So we will investigate a set of well-known intensity measures through the available recording. High spatial resolution of these recordings enables us to study the intensity measures, especially. To this end, we will perform kriging geostatistical analysis to the selected intensity measures to account for spatial variability across the Kereyjardy town. Then, as a part of Turnkey project, we constructed the building characteristic data bank for the Kereyjardy town in a dwelling by dwelling level of resolution. In Iceland, in the aftermath of a strong earthquake, such as the 2008 Olfos event, the Natural Catastrophe Insurance of Iceland estimates the losses of all damaged buildings to fulfill insurance claims. This allows establishing a damage database for all building units in the Kereyjardy town. So we constructed a detailed GIS-based database by collating these real loss database with the building exposure data. And at the end, we predicted losses using both global and local fragility models for the Olfos earthquake scenario. And this has been done in 2 spatial resolution. The higher spatial resolution refers to the building by building level, and the lower classical resolution is the municipality level, in which the whole Kereyjardy town is considered as one grid. And then the predictions are compared with the observed losses. In this map, you can see the location of the 2008 Olfos earthquake in the central South Iceland seismic zone. And also you can see the Kereyjardy town by red polygon. This town is a populated town and a tourist destination. And it has been hit by several destructive earthquakes, and the most recent one was Olfos earthquake. The town during this earthquake experienced intense near fall to strong motion, characterized by large high-frequency acceleration and large amplitude near fall velocity pulses, which was recorded on a small aperture ice array 1 station. You can see the location of the ice array 1 station by which is shown by yellow triangles. In this slide, you can see the spatial distribution of buildings over Kereyjardy, classified by year of construction and also by building material, as well as their corresponding histogram are shown on the above figures. Majority of buildings are low rise, and the number of stories are less than 2. A structural wall dominates the lateral load resisting system in nearly all buildings in Kereyjardy. Also, we should mention that only residential buildings in Kereyjardy constructed before the Olfos earthquake are selected for the analysis and comparison. Also, 47% of buildings are built before 1976, when the first seismic code was implemented in Iceland, and 22% of buildings are constructed after 2002, when the Eurocode was implemented. So the spectral acceleration for 5% critical damping ratio are computed from the processed waveforms of Olfos earthquake recorded by ice array 1 stations across Kereyjardy. The spectral acceleration corresponds to north-south direction, east-west direction, as well as the rotation invariant average of these 2 horizontal components. A spectral acceleration exceeds 1g over short periods of 0.1 up to 0.4 seconds. The recording stations were located about less than 2 kilometers from the vertical surface projection of the causative fault, and such distance can be considered negligible compared to the fault's length. And also from these figures, the large variability of spectral acceleration at period less than 0.6 seconds is clearly evident compared to the longer periods. We perform Kriging geostatistical analysis to generate shake maps and their uncertainty maps for a set of intensity measures. For instance, here you can see the shake map and the shake maps for PGA and its corresponding uncertainty map. This is the shake map for rotation invariant variable for a spectral acceleration at 0.2 seconds, and this is for a spectral acceleration at 2 seconds. At short period spectral accelerations, the central part of the town persistently exhibit lower acceleration values, whereas higher spectral acceleration values are indicated in the town's outskirts, while towards the longer periods, smaller values are recorded at, for instance, at outskirts stations such as IS 610, and also larger values are recorded at southwestern stations. Looking into the uncertainty maps, we can see that the spatial variability of intensity measures across such a small area is quite significant, and this proves the necessity of performing seismic risk assessment in higher spatial resolution, especially for South Iceland seismic zone in southwestern Iceland. To perform scenario-based loss estimation for residential buildings in Kerjerde, we first identify the building typologies according to the Sarah taxonomy system and assign them to each building and to each residential buildings. Here you can see in this table the building typologies as well as their label and the percentages of buildings in each classes. And then we apply the most recent global fragility models associated with the identified building typologies. And we compare the results from the loss results from these global fragility models with the recent local fragility and vulnerability models developed by Bessason for Iceland. The loss estimation has been performed in two resolution of building by building and municipality level, and to have an informed view of seismic risk, two sources of uncertainty, namely replacement value and ground motion intensity measures, are incorporated into the loss estimation through a logic tree framework. And finally, we compare these predictions with the observed damage values. As you can see in this figure, the mean damage ratio predicted using fragility models are shown for 8 building typologies. 3 bars represent first the high resolution prediction, the classical municipality level predictions, as well as the observation. Low ductility classes such as CL1 and CL2 results in higher losses than higher ductile buildings such as CM1 and CM2. For CL1 and CM1, which includes 48% of residential buildings in Kerjerde, the MDR estimates are slightly lower than the observed MDRs, which is shown by a yellow bar, while for the remaining typology, the predicted MDRs are larger than the observed values. As illustrated by small loss predictions associated with CL1 and CM1, the least vulnerable buildings are those made of reinforced concrete. However, masonry buildings with largest MVR is the most vulnerable building typology. When Olfos earthquake struck in May 2008, less than 7% of residential buildings were made of masonry. However, there are no longer masonry buildings built in Iceland, and this was an incredible promising risk mitigation strategy. In this slide, we compare the mean damage ratios from global fragility models with local fragility models. The local fragility models of Bessason 2020 are applicable to 3 building classes of concrete, timber, and masonry. Thus, the global fragility models are weighted based on the number of buildings in each classes to be comparable with the local models. Also, the observed MDRs are pooled for these 3 main classes. Based on the actual loss data, the timber and concrete buildings display the best performance during the Olfos earthquake, and the masonry building is the most vulnerable building class with the highest observed MVR. The observed MVRs combined for all buildings in Karagerdi is 4%, which is approximately half of the predicted MVR estimated based on the global fragility models in high resolution level. And the global fragility models perform better in predicting observed damages to concrete buildings in Karagerdi. In contrast, the local model performs superior in estimating damages to timber buildings across Karagerdi. In this slide, you can see the lower bound and upper bound of MDR estimates for one-story timber buildings, assuming upper and lower bound of ground shaking at the center of Karagerdi district, based on the classical resolution level, 23.5% and 4.3% of replacement cost values would be spent on repairing the buildings in Karagerdi respectively. To conclude, the results indicate that the buildings in Iceland show excellent performance during the Olfos earthquake, as the observed losses were significantly smaller than the predicted losses. The excellent seismic resistance of buildings in Karagerdi can be due to the fact that Icelandic buildings are constructed to withstand substantial lateral loads imposed by winds, because the prescribed wind force loads in Iceland are amongst the highest in Europe. Overall, masonry buildings are the most vulnerable building classes with the most considerable expected losses, and the global and local fragility models both tend to overestimate their associated expected damages in Iceland. Thank you for your attention.